Hey everyone. So now getting into chapter 6, most of the theory that we learned in chapter 3 is going to be directly applicable here. Um, and as I said, I'm skipping the first two sections just because they're kind of redundant on based on if you already have a pretty good grasp on chapter 3 in its entirety, you should be able to get by with not looking at the first two sections. So, starting with section 3, the overall arcing theme here is, can we expand what we know about 2 by 2 systems to 3 by 3, or really n by n? So let's consider as always our homogeneous linear system x prime is equal to ax, except now this time a is going to be n by n. So the solution is given as x of t is equal to c1 e lambda 1t times eigenvector v1 plus c2 e lambda 2t eigenvector v2. And for 2 by 2 that was all you needed. But as you go up higher in dimensions, then you'll have to add a c3 e lambda 3t v3. And so that would do it for 3 by 3. But if you go up to n by n, then you need n number of these. And so plus dot 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 plus cn e lambda n t vn. Now, this only works if all the lambdas are real and all the eigenvectors are linearly independent with respect to each other. Uh, Essentially the same thing as chapter 3, right? They have to be linearly independent between with respect to each other in order to form a fundamental set. Great. Now further, if a n by n has eigenpairs, where an eigenpair is just its eigenvalue with its corresponding eigenvector, lambda 1 v1, then lambda 2 v2, lambda 3 v3, etc., lambda n vn, then in each column, if you place e lambda 1 t v1, so that would be the first column, and then e lambda 2 t v2, that's the second column, all the way up to e lambda n t vn, thus constructing a square matrix. This is known as the fundamental matrix solution, which will play a huge role in I think about 2 to 3 sections here. So, as always, if you can remember, probably the hardest part about these problems is just that they're more involved computation-wise, but really you have everything that you need at your disposal to tackle them. But for completeness, I'm just going to go ahead and do one for you to make sure that we know what we're doing. Great. So if we're posed with this and we want to find the general solution, x of t, the very first thing that I've always said to do is just find determinant a minus lambda I. So simply determinant a minus lambda I. Now, for 3 by 3, it's different, right? So now this is going to be 3 minus lambda. Sorry about that. 3 minus lambda, 2, 4, 2, minus lambda, 2, 4, 2, 3 minus lambda. Okay, now this, the definition for determinant is recursive, as hopefully you know from linear algebra and potentially Calc 3. And so what happens is you basically break it up into smaller 2 by 2s. But you go along a row or a diagonal in the matrix to decide. So I am going to go ahead and do the first column as my row. So what this means is I take this term and then I kind of cross these two terms out. And so then these 4 terms are what's really going to be my determinant. So I'll write this out for you. So what this means really is, based on the recursive definition, it's 3 minus lambda times the determinant now of minus lambda 2, 2, 3 minus lambda. And then you keep going. So I said I was going to do the column, so now it's this one. And so what happens now is that the this is the one that is of interest. So we cross here, which means that now, what means now is that the 4 terms of interest are now 2, 4, 2, and 3 minus lambda. And remember, as you go down the column, you have to alternate in sign, which is encapsulated by the -1 to the n plus 1 formula for determinants. So this means this is really minus 2, and then determinant of 2, 4, 2, 3 minus lambda. Lambdas are not good today. And then you deal with the 4. The 4 is just going to be positive. And then it's going to be 2, 4, minus lambda 2. Great. And so, yeah, so now you have to deal with 3 determinants. So it can get a little heavy computation-wise. But that shouldn't deter you from solving these. So for the first one, I should probably keep some of it up. Okay, cool. So for the first one here, that first 3 minus lambda times the determinant of minus lambda 2, 3 minus lambda, that comes out to be 3 minus lambda, right, multiplied onto minus lambda, 3 minus lambda, and then it's minus 2 times 2, which is minus 4. So that's the first part. And then the second determinant, right, is minus 2 times the multiplication of this. So 2 times 3 minus lambda. And then this is a minus 8. And then the fourth one is just plus 4. And then it's 4 plus 4 lambda. And then, again, determinant a minus lambda I has to equal 0. So all of this should be equal to 0 in order to find our eigenvalues. I'm going to go ahead and skip a little bit of algebra just for time's sake. You can factor this out and try to arrive at the polynomial that I'm going to just arrive at right now. And that polynomial would be minus lambda cubed plus 6 lambda squared plus 15 lambda plus 8 is equal to 0. Great. So this should make sense to you. This is n by n, and in particular it's 3 by 3. It makes sense that our characteristic polynomial is of third order. If you think back to chapter 4, if we had a third order system, or a third order differential equation, right, and we try to make it into a system, it would be a 3 by 3 system, right? And the characteristic polynomial of that third order diffq would also be third order would result in a 3 by 3 system. So this makes sense. If you only had something that was second order, something is wrong. If you had something that's fourth order, something is wrong. So be careful to check for that. Now, a lot of you and many students in the past before you have asked me, okay, how do I factor this really? Because there's no set way of factoring powers greater than 2. And so the first thing that you would want to do is try to see if you can group things together. But as you can see here, that's not really possible. So the next thing that you do, and hopefully you remember this from high school, I think, is that the rule that the possible whole factors that can be part of this equation are exactly the plus or minus factors of the lowest order term divided by the plus or minus factors of the higher order term. So what does that mean? This means that, okay, the factors of 8 are plus or minus 1. Positive and negative factors, sorry. Plus or minus 2. Sorry, I kind of messed up right there. Plus or minus 4. And plus or minus 8. And then the factors of this, the lambda cubed, is just, it has a minus 1, so it's just a plus or minus 1. So this means that the only possible whole number factors, if they exist, for this polynomial can be plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. Dividing by plus or minus 1 does nothing, right? And so feel free to try these to see what lambdas satisfy this. And to go ahead and save some time, I've already done that for you ahead of time. So the lambdas here that work are 8. And then minus 1 has a multiplicity of 2. Great. Alright, time to get into the tricky stuff, well, not really tricky, just tedious, of row reducing. So I'm going to take lambda equal to 8 as the first thing that I want to go ahead and try to find the eigenvector for. So lambda equal 8. That means I'm going to do a minus 8I times v1 has to equal 0, right? That has to happen. Great. So from the matrix above, hopefully you've written it down. If you do subtracting 8 across the diagonal, you're going to get that the matrix becomes minus 5, 2, 4, 2, minus 8, 2, and then 4, 2, minus 5. Okay. Now, your goal is to just row reduce this as far as you can until you can manipulate the equations in order to find the eigenvector that satisfies this. Okay? Really, just start off with wherever you can to start finding your pivots, as in just try to make as many numbers as you can go to 0. And that's really as much as I can tell you. Hopefully, in linear algebra, I know at Georgia Tech they make you do this a lot for linear algebra, so you should be able to at least remember how to kind of do this. But I'll walk through this first one, and just as a disclaimer, I'm never going to do it again, just because it takes way too much time, and I think we can use our time more wisely just on theory and really understanding the heart of differential equations and not just tedious algebraic manipulations. So let's just get started. The way that I write this also is, so the first row reduction to me that seems obvious is minus 2 R2, which means the second row, plus R3, and then I write it as an arrow R3, which means that I'm going to do minus R2 plus R3, and it's going to go on to R3, as in the row that's ultimately affected is R3. So if you do that, first row is unaffected, right? So it's minus 5, 2, 4, and then minus 2 R2 plus R3. Again, second row is not going to be affected as well, but the third row is. So minus 2 times 2 is minus 4 plus 4 is 0, which is what I wanted. Then this other term right here becomes 18. Minus 2 times minus 8 is 16, plus 2 is 18. Minus 2 times 2 is minus 4, plus minus 5 is minus 9. So that's good. And then you just keep doing this up until you're good, right? Next thing that I want to do from here is, I see this 18 and minus 9. I'm going to go ahead and do a 1/9 R3. You can write the onto R3, but it seems pretty obvious. That's what I want to do anyway. So then this becomes, again, first and second row are not affected by this operation. So this becomes 0, let's see, 2 minus 1, right? Cool. Next thing that seems obvious to me is 1/2 R2, because they're all even. So minus 5, 2, 4. Third row is also unaffected, 0, 2, minus 1, and then second row is affected, so it's 1, minus 4, 1. Great. Next thing that I want to do is probably get rid of the first element in the matrix. So to do that, I would want to add 5 R2 onto R1, plus R1 onto R1. So, and then to go from there, to keep going, so giving myself some more space coming down here. This row reduction, so the first row is affected, which means second and third are not. So 1, 0, minus 4, 2, 1, minus 1. The top row then is going to go to 0, minus 18, and then 9. Cool. Again, let's do a 1/9 R1, and that is onto R1. So first row is affected, so 0, let's see, minus 2, 1, 1, minus 4, 1, 0, 2, minus 1. From here, what I want to do now is probably add R1 onto R3. That seems good. So R1 plus R3 onto R3. That is a terrible 3. I'm so sorry. 3. There we go. Okay. So what that's going to result into is, again, first and second rows are unaffected. This pen does that a lot. It just like connects the top of the number 4 and the number 9, and well, I want the number 9 connected, but number 4 is a little annoying. But I digress. That then becomes 0, 0, 0. That's pretty good. Alright, great. So now we really only have to deal with the first two rows. And from here, what I want to do is minus 2 R1 plus R2 onto R2. Great. So then this becomes, again, 0, minus 2, 1, and then we have our row of zeros. And then this becomes 1, 0, minus 1. Now, to me, that is perfectly fine. I don't care about row reduced echelon form or whatever, what might have you. If you're genius level and you can find the eigenvector without a calculator from that first matrix that we have right there, go right ahead. Keep in mind, most TAs wouldn't find any way to give you partial credit if you're wrong. But to me, this seems perfectly fine. So from what you can do here is what you've done always. You can just rewrite what these equations really mean. So that first row, what it's telling you is that minus 2 v2 plus v3 has to equal 0. Yeah, see, that's the other one. It's the equal sign. Gets connected a lot. Alright, equals 0. And then down here, it's v1 minus v3 is equal to 0. And then, really, this bottom row implies v3 can be whatever. Or if you want to be more correct, it's a free variable, whatever. So, what seems obvious to me is, let's make v3 1. Actually, no, let's make it 2. Let's make it 2, yeah. 2, which means, as per this equation in the middle, v1 has to also be 2. And then the reason I wanted to make it 2 is because then if minus 2 v2 plus 2 has to equal 0, therefore v2 has to equal 1. And so therefore that is your first eigenvector. Cool. Now, you do the same thing with your other eigenvalue that has multiplicity 2. Again, you've done this hopefully for quite some time now. And so initially what this matrix now becomes is 4, 2, 4, 2, 1, 2, 4, 2, 4. And then this row reduced goes to 2, 1, 2. Again, I told you I was never going to do it again, just because that took a lot of time. But I did want to show you how to do it just in case. And so now you may be thinking, alright, do we need to find like the W vector? Like what happens now that we're with multiplicity? Not necessarily. I would say to first write down the equation that this implies. So this is 2v1 plus v2 plus 2v3 is equal to 0, right? Okay, now let's ask ourselves. We can find a second eigenvector, well, the first one corresponding to this eigenvalue, as, let's see. What if v3 is 0, right? Let's make v1 equal to 2, or 1, sorry. And then therefore v2 has to be minus 2, right? That's perfectly valid. Now, can we construct another eigenvector from this? Keep in mind, the only way that this can work is if v3 and v2 together, they're linearly independent with respect to each other, which is why this works, okay? So from here, let's make v3 a number besides 0, so let's say 1. Then let's make v1 0, which would imply that v2 has to be minus 2. These two vectors are perfectly valid, which means no, you do not need a W vector, and you can just roll with this and make it part of your final solution. So, from here, you can go ahead and write down your final solution, which is great. So, final solution, tying everything together, x of t for that matrix would equal c1 e to the lambda 1t e8t, right? And then our eigenvector was 2, 1, 2. plus C2 e to the minus t times this second eigenvector, first corresponding to this eigenvalue, 1 minus 2, 0, and then plus C3 e minus t, 0 minus 2, 1. And that is your final answer. Great. So next time we're going to start dealing with matrices that have complex eigenvalues, and again, it's the same idea. We're just going to reuse what we've already learned and just apply it to higher order systems. So, see you then.